Welcome to lecture 21 in our class on stochastic processes. Today we will discuss and prove the Ito formula, which is a very important lemma which has an enormous, unlimited amount of applications and practical applications of stochastic calculus. And we will then enter the discussion of the Black-Scholes model of financial mathematics, which is a super famous and very important core model of financial mathematics, which demonstrates or which gives a very nice field of application for the theory of stochastic differential equations that we have learned so far. Namely, we'll discuss the basic model of the Black-Scholes world, which is a model for the dynamics of the stock price, which is slightly more complicated than a simple Brownian motion that comes with a certain stochastic differential equation. It will be the first moment when we will see a stochastic differential equation, and we will show that geometric Brownian motion is in fact the solution to the Black-Scholes stochastic differential equation by applying the Ito formula. So that will be the program of today, and in lecture 22, which is the next lecture, we will discuss the Black-Scholes model and its implications for the price of certain derivatives of stocks in full rigor, which will be then the conclusion of our little excursion into financial mathematics world. Okay, we start with the discussion of the Ito formula, which is a chain rule for what happens when you have a certain semi-martingale. We call that the semi-martingale is a superposition of a martingale with a process of bounded variation. And so the Ito formula deals with the process which you get if you insert such a semi-martingale, which may be a semi-martingale in several dimensions, into a real valued function of sufficient regularity. That will be the Ito formula, and the core, or the basically most simple version of the Ito formula, is the so-called integration by parts formula for stochastic integrals. And we will use this integration by parts formula in order to show the Ito formula in full flavor. So let's start with the so-called integration by parts formula, which is the first result of today. The statement is as follows, namely that x and y be two continuous semi-martingales. So two stochastic processes which are defined on the same probability space with a filtration which is indexed by the continuous non-negative time axis. And then we can look at the process which is obtained by pointwise multiplication. So think of two stock dynamics, x and y, and by whatever reason you are interested in the product of the two values. So then the process which you look at is the product process. Namely, at each time you do the simple product multiplication, and then it says that we can retrieve this product values by performing a certain stochastic integral, a collection of stochastic integrals. I mean, it says that the product of the two stochastic processes at time t is the same as the product at initial time, plus corrections which come from the time evolution in between the two times 0 and t. Namely, what you have to do is you have to integrate the x process with respect to the y process up to time t from 0 to t. You have to integrate the y process against the x process in the sense of stochastic integration. That would be basically something like a Leibniz rule. If you think of these two functions or objects as functions in time, what you see here in the first part of this equation is just, in a way, the Leibniz rule, the famous Leibniz rule for the derivative. So that would be a plain application of Leibniz rule in the case when these two processes were differentiable, in fact, in time, which they are typically not for stochastic processes. And then there is a correction term to this Leibniz rule, which is the new feature of this theory, which is that you have to correct this Leibniz rule by an additional term which measures the co-bracket or the quadratic covariation process of the two processes x and y. So if you look at this formula again, it's the integration by parts or product rule for the product of two semi-martingales. It says that if you have something like a chain rule for the product operation, chain rule with respect to the time derivative, if you like, but the chain rule comes with a correction, and the correction is exactly the co-bracket or the quadratic variation process. That's the integration by parts formula, and we will later extend this integration by parts formula to give a very powerful, much bigger theorem, which is then the Ito formula. Okay, let us prove this integration by parts formula. In the simple case, when x and y are the same. So these expressions here, this is a bilinear, the formula that I want to prove is a bilinear formula with respect to the two components x and y. And so by polarization, as we had done before already, it is sufficient to prove the formula on the diagonal, if you like, when x and y are the same. So what I want to compare is the square of the x process at time t with the square of the x process at time 0. Okay, and if I pick a certain partition of the time axis by a simple telescope sum argument, I can represent this difference at the endpoints of this macroscopic time interval by the sum of increments on the squares on these intermediate time points, just telescope sum, and then by binomial formula, this difference of squares on these different time points can be written like that. And finally, since I like the term when here, so I like this term here on the right hand side. So the second factor I like because it seems to it reflects an increment. So that's a good thing. I'm kind of familiar now with increments. And I know that somehow I know that there is a limit statement for stochastic integration, like dominated convergence, for instance, that we discussed, that if I multiply the increment of a certain process with the value of the process on the corresponding left endpoint on the interval of the respective interval. So therefore, I like this part of this product I like a lot. And this term here causes me some trouble. So in order to so that's why I single out this part first, and I add one more of this sum, which produces effectively a minus sign as a correction in the second part of the sum. By this simple manipulation, I have converted this sum of a sum and a difference into twice this prototype of a stochastic integral plus the sum of the squares of the increments. And now I have two terms or two sums which I can understand very well. For both of these terms, I have a limiting statement, namely this sum of the increments is clearly the thing that converges upon finer and finer time grid towards the stochastic, towards the bracket process of x. And the first component here is by our dominated convergence theorem, if you like, of stochastic integration, using also the continuity, if you like, of the x process. It converges to the stochastic integral of the x process against the x process itself. So you see that using our limiting properties of these increments, we obtain easily the claim which is in the lemma in the case when x and y coincide. And as I just said, the claim when x and y are general or different probably is just obtained from the previous case by polarization. Now, using this integration by parts formula, we will now be able to prove the Ito formula. And the Ito formula deals with a much more complicated case, but is reduced to this integration by parts formula, which we have just discussed. Now we want to consider the case of D stochastic processes, which are all each semi-martingales. So if we write them as coordinates of a d-dimensional process, this is what we would call a continuous semi-martingale in dimension d. So that's the x process. Before we had d equals 2, an x and a y process. And I want to consider a general function which combines these d different processes into a new process. So the function f, which is used as a recombination of these processes, is of course a map from d-dimensional space into the reals. And I want to assume that it is C2 regular. So it has two derivatives and all derivatives are continuous. And I want to consider now the process which is obtained by, as I just said, inserting this d-dimensional semi-martingale into this evaluation function f of general type. And the statement is that this new process is again a continuous semi-martingale. So it's not a totally arbitrary process. It's again a process which can be decomposed into a martingale and a process of bounded variation. And we have the following representation of the macroscopic macroscopic changes of the Z process. Z, recall, is the process which is obtained by inserting into the f function these d different processes. So if I want to compare this Z process or Z process at different times, of course it's just these difference of these f evaluations, but I can obtain these difference of these f evaluations also by doing something like the fundamental theorem of calculus. I can take, if you like, the derivative of all this quantity with respect to time and then integrate back up again the time. So this is, if you like, a version of the fundamental theorem of calculus with an additional correction term. Okay, so what would we expect from standard calculus? We would obtain that we have to take the derivative or to take the sensitivities of this exterior function f with respect to all the arguments, and take the derivative or take the integral with respect to the changes in value of the input data. So we have to take each of these partial derivatives of the function f with respect to the respective variable, with respect to the respective input datum. We evaluate this partial derivative and integrate this partial derivative with respect to the time change or the change in time of the corresponding input datum. So it's the kth partial derivative of the function f, which needs to be integrated against the changes in value of the kth input datum. If we sum that up and integrate, and if we sum up all these integrals of changes, of value changes, then we would obtain the total change of the f observable in this macroscopic time interval. But since we have non-differentiability, we have to be ready to accept the correction to this formula. Let me say it again, this formula would be exactly the formula that you would expect from conventional fundamental theorem of calculus in higher dimension. And the correction term is what we later will call the Ito correction, will be a term which deals with the co-bracket processes of these input processes. Namely, we have to take the second order derivative of this exterior function in all possible choices of second order derivative directions, which means we have to take the full Hessian. So that's the Hessian, the entry of the Hessian matrix of the function f at coordinate k and l. We evaluate this at the location of the process, and we have to integrate this, this is now just a continuous function, a function in time parameter s. We have to integrate this continuous function for this choices k and l of parameters. We have to integrate this against the co-bracket process of the kth and the lth input process. This comes with a factor 1/2. And that's the Ito correction. So we see again that we have not quite the statement of the fundamental theorem of calculus. There is a correction to the fundamental theorem of calculus which deals with the second order correction. And the second order correction, or the correction on order of second order, features exactly the co-bracket or the quadratic covariation of the input data. So in this regard, it's quite a spectacular, if you like, completely novel formula, which you do not see if you do not consider stochastic processes or so, when you have non-regular dependence in time. And in case of semi-martingales or martingales, we have a well-defined quantity, which is the co-bracket, which measures exactly the deviation from the standard fundamental theorem of calculus, which is correct, but it's correct only in case when the trajectories are really differentiable. Okay, you might understand already now that this is quite a significant result, which shakes up things quite a bit in the stochastic world, obviously, because you cannot rely on your intuition of first order calculus anymore when you deal with continuous time martingales. Okay, we prove this formula, and you will see that it's surprisingly simple to prove it. Namely, we start first by considering the case when the function f is just a polynomial. And here we can prove the statement by induction on the degree of the polynomial. For instance, if we have just a plain linear function, so degree 1, then there's nothing to prove. because the derivatives are constant or vanish, and it's just a linear transformation of processes, so there's nothing to say. The case n equals 2 is exactly the case when you take a polynomial of order 2. It's just exactly the product rule, which we have just discussed. It is the question of how does the product of two semi-martingales evolve over time, and that's exactly the formula that is the integration by parts formula, which we had just seen. So let's then deal with the induction step, namely assume that we have proved the formula for a certain polynomial of a certain degree, and then we just multiply this polynomial with a certain monomial of order 1, namely just the coordinate function of coordinate k. Then we compute the derivatives of this g function. Well, if you take the derivative with respect to the g, so here my notation will be in the future that a partial derivative of a function in d dimension or high dimension will be denoted by just a comma with the index of the direction in which I do the derivative. So if I compute the ith partial derivative, the derivative in the direction I of this thing, then I get a Dirac delta depending on whether I coincides with k. And of course, then I get the xk times the fi, the partial derivative in I direction. And similarly, the derivative of g in the second order derivative in direction I and j is a sum of two Dirac terms, which appear depending on whether you have whether the I or the j index coincides with a k. And then you get the xk as a prefactor times the usual second order derivative of the function f. So this is just a straightforward chain rule or product rule here. And then I want to make a statement about the evolution of the quantity of what I observe when I input the x process into this g function. Well, the g function is a product of a monomial with an f function, which I had understood. So therefore, I call this monomial, just for the fun of it, ut. So it's just my process in the kth coordinate here. I call it just ut, just to make it clear that I connect now to the integration by parts formula for product case situation. And I call the f of xt process vt. So therefore, this evaluation of this g function on the two different time points can be reduced to the evaluation of a product of two processes, where u is just the kth coordinate and v is the evaluation of the x process by means of the function f, which is of degree n. Now, since I know by the statement that the f function is a semi-martingale, it's part of the statement, I can apply the previously proven product formula or integration by parts formula for this product of two semi-martingales, which tells me that this difference of these two values over time can be obtained by doing an integration according to the Leibniz chain rule, but with a correction which involves the bracket process of u and v. So let me call these three different terms which appear here 1, 2, and 3. And before I evaluate these three terms further, let me have a look again at the v process, which appears here. Well, for the v process, by the previous induction step, by the previous induction hypothesis, the v process is a polynomial of degree below, smaller, and there I have the Ito formula, which tells me that the v process changes from the process v at time 0 by performing an integral according to first order chain rule. And here I'm using, for simplicity, because here in this case it's easier, I'm using this dot notation. So I need to integrate the partial derivatives of first order of this f function with respect to the corresponding coordinate processes in the sense of a stochastic integral. And then I have to do this second order correction on the f function, which involves all second order derivatives, all combinations of second order derivatives of the f function with a factor 1/2. With all the where I have to take the Stieltjes integral against the co-bracket of all these corresponding coordinate processes which appear here in this combinations of directions. Okay, so the V process is a superposition of a certain stochastic integral, or the sum of a certain stochastic integral and an integral in the Stieltjes sense, but nevertheless it's a generalized Stieltjes integral. That's how we wanted to understand the stochastic integral after all. And so the first of these three terms which were appearing, the first of these terms involves an integral of the U process against the V process, where the V process is a sum of integrals. You have seen it here just now. And so what we do effectively here is that we take an integral of a process which itself is an integral. And so by the associativity of the stochastic integral, we know that the integral against an integral is nothing but the integral against the integrator on the lowest level times the product of those processes which were integrated. So in other words, ut times dvt is the old ut process, which was the kth coordinate process, times, for the first part, f L derivative, a derivative into L direction of f, integrated against the xl process. So here I'm pulling these two integrations, writing them as one, using the associativity, as I mean again, associativity of this stochastic integral, where I need to integrate the product of the two processes, namely the u process is the one factor of this product, and the second factor is the lth derivative of the f function evaluated on the x process. Okay, so that's one summand. Then I have the second summand. The second summand comes, again, the v is a sum, so the dv, the increment of the v process, contains also an increment of this component. So therefore this comes in here with the one factor 1/2 that's inherited. And again, I'm applying the associativity here in this case of a plane Stieltjes integral, where here again the u process needs to be multiplied with these second order derivatives. The u process was the kth coordinate of the input vector times the second derivative, and then this needs to be integrated against the corresponding bracket. And the factor 1/2, as I just said, of course, goes to the front. So that's in total what I obtained for the first of these two summands. For the second summand, that's this integral here. Well, v is just the function f applied to the process x, and u is just the coordinate k. So therefore, the second summand is just the stochastic integral of the f on x processes against the kth coordinate process. And what about the third? The third is a co-bracket of the u and the v. Okay, so the v, as I said just before, the v is a sum of two things. So therefore, by linearity, the co-bracket of the k with the sum is just the sum of the corresponding co-brackets. So therefore, I just decompose this sum of the, I just have the sum of two different co-brackets. Well, I have more than just the sum of two pieces, but okay, of course, yeah. Okay, and here the important observation is that the second part, the second component of this co-bracket is a zero. Why is this? Well, this integral here, or this process which is obtained here, is a process which is obtained by a plane pathwise Stieltjes integral against the co-bracket process, which is a process of bounded variation. So therefore, the plane Stieltjes integral as a function on time is again a function of bounded variation. And so the quadratic variation of this process is zero. And by, if you like, Kunita-Watanabe identity or inequality, the co-bracket of a process of the co-bracket of any process with a process of bounded variation is zero. That's true for all possible choices of coordinates L and M, so therefore this is just a zero, and there's only the first summand remaining, which is again by associativity of the Stieltjes integral, or in this case I should probably better say this is the fundamental rule for our stochastic integration. If you recall that the co-bracket of any stochastic integral with respect to another stochastic process was just the same as the Stieltjes integral of the integrand against the bracket, the co-bracket of the integrator with the corresponding second or test process or test semi-martingale. Okay, so that's the process, that's the component 3. And if we plug all these things together and sort terms according to whether they contain a bracket or not, we obtain first the non-bracket part, which is this, and then we collect all the brackets. And if we compare these expressions to the expressions that we had for the algebraic expressions for the second order derivative of the function g, we see that this is exactly the formula that comes out accordingly. So that is the induction step for the polynomial case, and we have proved therefore the Ito formula in case when the outer function f happens to be a polynomial. For general function f, which is sufficiently regular, the final step is the reduction to the polynomial case by approximation. For that, we shall now assume that the function f is only C2, smooth, and we we take a collection of compact sets which are increasing and exhaust the full Euclidean domain. And we introduce the stopping times for the process x for our semi-martingale, which correspond to the first exit of those compact subsets. Now we consider then the process xn, which is just the stopped, process x at the stopping time, stopped by means of the stopping time with index n. So if we stop at stopping time as a semi-martingale by means of a stopping time, then the result is still a stopping time. It's still a semi-martingale, and of course that semi-martingale then by construction assumes only values in Kn. So this semi-martingale never leaves the compact set Kn. Okay, then by some approximation theorem like Weierstrass approximation theorem, but now with respect to the C2 norm, so slightly more complicated, but in fact not so much more complicated version of the Weierstrass approximation theorem. If we restrict the function f to the compact subset Kn, we can find a sequence of polynomials which approximate with respect to the C2 norm, so including also the second derivatives and first derivatives in L infinity norm, which approximate the f function on that compact subset. And we have, of course, for the PM process, we have the Ito formula, or the claim, in case when the function f, or when we just deal with the PM functions instead. M is the index for approximation of the function f. So we have the formula. And, we evaluate this formula as long as we deal with the process up to level n alone. Of course, this is just as good by the properties of the stochastic integral with respect to the stop process and so forth. We can just move this stopping that we apply to the process x. We can also move it just to the upper boundary of the corresponding stochastic integrals, because that's a property that we have seen already a couple of times. Conducting an integration with respect to a process which is stopped is just as good as doing the full integration against the process, but stopping the integration at that moment of the stopping. So therefore we can just move the stopping up to the upper boundary of the integration. And if we integrate only up to the stopping time, here's a little misprint, then we don't actually see any difference between the x trajectories and the stop trajectories. So therefore, in the inside of these integrations, we can just write the unstopped process. Okay, and now if we take this approximation index for the function f to infinity, or in other words, if we choose better and better polynomial approximations in the sense of the C2 norm, which in particular implies that also the derivatives of the PM polynomials converge to the corresponding derivatives of first and second order of the function f by dominated convergence for stochastic integration, for instance, we see that all of these integral terms on the right-hand side of this equality converge to the corresponding integrals when the function f is appearing with its derivatives, and on the left-hand side by convergence in pointwise convergence alone. We, of course, can also pass to the limit. So therefore, we have the formula for a general function f, which is C2, at least as long as we stop the process by means of a certain stopping time. But this is exactly the same as saying that this process f, if we stop it by means of appropriate stopping times, has exactly this representation, which is therefore exactly the claim that, namely, this combined process has a representation on the right-hand side whenever we stop, but this sum of processes on the right-hand side, the sum of these stochastic integrals, define in a unique fashion a local, a semi-martingale. So therefore, we have effectively established the claim. So for all possible stopping times, you have this correction. There is a sequence of stopping times which diverges in a monotone fashion towards infinity, such that this equality is correct for all these stopped processes, or for all, as long as we consider the process only up to these stopping times. And this means exactly that the process, the composition of the process x with the f function is a local semi-martingale and has this representation. So that concludes the proof of the Ito formula. And as you have seen, the core argument was the reduction to the polynomial case, respectively the reduction from the polynomial to the case of a simple product rule. Actually, before we start discussing as a nice and funny application the Black-Scholes model, I have another application to prove a result that we already know. But I want to give it a different proof now using this Ito formula. Namely, the example I want to consider now is the case when the x process is just d-dimensional Brownian motion. So in a way, it's the cleanest or the most natural d-dimensional Euclidean semi-martingale, which is just a d-dimensional Brownian motion. So each of the coordinates are just a one-dimensional Brownian motion, and the coordinates are independent. And then it is true that also the product of these two coordinate processes is a martingale, for instance, with respect to the filtration which is generated by the Brownian motion, in case when the two coordinates are different, which is a lemma which I shall prove below. It's more complicated than it seems at first sight. So the lemma says that if you have two martingales and the two martingales are independent as stochastic processes, then the product process of the two is also a martingale. And in particular, it implies that the bracket as a corrector, the bracket of two coordinates of Brownian motion, is zero, because you don't need any corrector in case when the two coordinates have different indices. But whenever the coordinates have the same index, so when I equals j, then the square of a plane Brownian motion, of a standard Brownian motion, is not a martingale, as we know. And the corrector in this case needs to be the identity process in time, so just the t process. So in other words, these brackets which appear in the Ito lemma for all different coordinates, they all disappear except when we deal with brackets which deal with with identical indices. So let me say it again: the bracket of the coordinates of Brownian motion is zero unless the two coordinates happen to be the same, and in this case the bracket, of course, is just the identity as a function of time. And so if we apply this Ito lemma to the case, as I just said, that this d-dimensional process is Brownian motion, then by plain application of Ito formula, we have a decomposition or a representation of the evolution of this observed quantity according to a corrected fundamental theorem of calculus, which says that I have to take this have to integrate the gradient of this observable function f against the increments of the Brownian trajectory. This is an integration in the sense of a stochastic integral. We had invested a lot of time to understand this. And then I need to include a second order correction, which involves the second order derivatives of the function in all possible directions. But I have written here already a shortened version, or the effective equation in this particular case, because here, if you recall, hypothetically, all different possible combinations of second order derivatives of the function f might appear. But since the brackets which I have to integrate against will vanish for all choices of coordinates which are different, only the diagonal terms will remain, and I'm having only the bracket of the corresponding diagonal squares, and that in each case is just the increment or the identity function in time. So therefore, this just is the conventional ds integral in this case. And here I used a shorthand notation, by the way, which I sometimes will use in the future, that if I say that I'm integrating a vector-valued stochastic process against another vector-valued stochastic process, what I mean by this is that I take each of the coordinates of the integrand, which in this case will be the partial derivatives of the f function, and I integrate that against the corresponding coordinate of the integrator, and I take the sum of this. So that's my shorthand notation for this first part of the Ito formula, just a chain rule, if you like, the standard chain rule. Okay, so let me say it again. So in case when my d-dimensional stochastic process is just Brownian motion, my Ito formula will simplify, and in particular, I see that the gradient term here, as usual, the gradient term here with the sum of integrands against the Brownian motion in each coordinate is the sum of integrals against the martingale, which we know is a local martingale. So therefore, I have a martingale term, which is the first order correction. So the first order correction here will be a martingale term, and that's not the first order correction. So the chain rule here, the Ito formula here has a term of first and second order, and in this particular case, the first order term is just a plain martingale, and the second order term is a ds, it's just a ds integral, which involves the Laplacian of the function, because here I'm basically, or effectively, only evaluating the sum of the second order derivatives of the function f in each coordinate direction. That's the Laplace operator. And in this way, we retrieve, using this time the Ito formula, that if we have a function f which is, for instance, twice continuously differentiable, and if it is harmonic, then the composition of f with a d-dimensional Brownian motion is a local martingale. We had this already proved by different means, by using, for instance, the Markov property and the exact semigroup property of the semigroup analysis of the Brownian semigroup. Here we have a different proof, which uses just the Ito, which uses the Ito formula. So the previous argument used the fact that the product of the coordinates of a d-dimensional Brownian motion is again a martingale, which yields the fact, so in case when the two coordinates are different, which in particular means that the co-bracket of these two coordinate processes is zero. And that's why in the Ito formula for Brownian motion in d-dimension, we see only second order derivatives along the diagonal of the outer function f. And we can phrase this auxiliary statement as a separate lemma, which can be done like follows. So if you have two continuous martingales which are independent and which are martingales with respect to a certain continuously time indexed sigma filtration, then in fact the new process, which is obtained by taking the pointwise product, that is again a martingale with respect to the same filtration. That's in my view, a more complicated statement than it seems at the beginning, and it involves 2 or 3 little arguments that I want to sketch, and I would like you to complete some of the details by your own, or just recapitulate themselves. So we first reduce the case to the situation when we deal with the filtration which is generated by the 2 processes. Okay, the martingale property in particular implies that the filtration which is generated by either of the 2 processes is a sub-filtration of the given filtration. And I want to show now something that I should have probably discussed already before, that if you have a martingale in a certain filtration, then the process will be a martingale in its own filtration. Also, let's prove that, namely, if I compute the conditional expectation of that martingale, M, let's say, with respect to its own filtration at a previous time, then since this filtration here is coarser, I can first project the same random variable to a finer filtration, a finer sigma field, which is the full F sigma field at the same time as, and then in a second step project to the coarser sigma field. That's just the usual projectivity property of conditional expectations. Now I use the fact that the M process was assumed to be a martingale with respect to the filtration, the primal filtration, so the full filtration. So therefore, this inner conditional expectation is just the MS, is just the martingale at time S. The outer conditional expectation remains. So here I'm computing the conditional expectation still eventually now of this MS process, MS random variable, given the sigma field, which is generated by all these M's up to time S. And of course, that's just MS because MS is trivially measurable with respect to this sigma field. So, and again, by martingale property, I can write this back again as just the plain expectation of that martingale at time t conditioned onto the correction here. I wanted a conditional to the sigma field M correction F. Okay, so I find that the conditional expectation of that martingale, given the sigma field which is generated by the process M alone at time S, is just the same as if I compute the conditional expectation of the martingale given the full sigma field Fs. That's just a little auxiliary consideration that I will use a little later. The second auxiliary consideration that I want to include is that if I have 2 random variables, call them x and y, on a probability space, and if I have 2 sigma fields, g and h, sub-sigma fields of f, of this, and if the pair of random variables x with the sigma field g is independent of the random variable y and the sigma field h, which means that all possible indicator functions belonging to sets of g multiplied with the random variable x and then taken into other transformations, this will be independent of the corresponding variety of random variables which I can construct from indicators of h and the random variable y. So I could also phrase it in a different fashion. I could say that the sigma field which is jointly generated by g and x is independent of the sigma field which is jointly generated by y and the sigma field h. So that's my independence assumption here. Then the conditional expectation of the product of the 2 random variables given the sigma fields which are jointly generated by g and h is nothing but the product of the 2 respective conditional expectations. So in other words, I'm saying that in a way if both the sigma fields g and x on the one hand and the sigma field h and the random variable y if they are as pairs independent, then the conditional expectation of the product factorizes like this. That's what I'm saying here. And it's a simple exercise to prove that this is actually the case. Okay. In the case of the martingale problem that I'm having, I consider now the question whether I can, so that can be applied to the situation when I want to compute the conditional expectation of the product of the two martingales given the sigma field which is generated by the two stochastic processes up to time s. And a straightforward application of the previous lemma and the independence to the case that these processes are independent, so therefore these jointly generated sigma fields or these individual sigma fields are filtrations are independent, together with the martingale property of M and N, directly leads to the conclusion that this product, that this conditional expectation of the product of these two processes, when conditioned onto this sigma field, which is jointly generated by the two processes M and N up to time S, is just the product of the two random variables MS and NS. So in conclusion, as the first intermediate finding, I convinced myself that if I have two independent martingales, then the product of the two independent martingales as a new real-valued process is a martingale with respect to the filtration which is generated jointly by these two processes. As a consequence of this, I find that if I work with martingale theory relative to this filtration, that the bracket process of these two martingales is zero, because I don't need any compensator. Recall that there is a unique compensator, which is the process starting in zero of bounded variation, which converts the product of the two processes into a martingale. But since the product is already a martingale, I don't need any. And by uniqueness, the compensator must be zero. But on the other hand, the compensator is obtained independent, is in the end obtained without making any reference to any kind of filtration, as the locally uniform limit in probability of this squares of increments of this M process, or in this case, in the bilinear case of the products of the relative increments. So, in particular, since this bracket process construction is good for any continuous parameterized filtration, I find that also if I work with this finer filtration F, and I construct the corresponding bracket process there, I find that also with respect in this finer filtration, I need no compensator, or in other words, the compensator is just a zero process. So therefore, the product of the M and N is a martingale also in this finer filtration. Okay, so that's quite a complicated proof for a statement which at first hand seems quite intuitive, and the core of this argument here, at least in the way that I could figure it out, is the fact that we have a statement about the compensator that it exists without making any reference to the specifics of a filtration. We just need to have that each of these processes, M and N, need to be martingales in a continuous filtration, and then we already can conclude that this bracket process can be obtained by exactly this procedure, and it will be the compensator for the product of the two martingales in any filtration, effectively, provided that each of the processes is a martingale in that given filtration. Fine. We will now give an application of this Ito formula in the case of the Black-Scholes model, which is the paramount model in mathematical finance, for the evolution of a simple stock on the stock market. The Black-Scholes model comes with two important parameters. One is the sigma parameter, and the other parameter is alpha, which is something like the exponential growth rate of the stock, and sigma is called the volatility. And S naught is the initial value of the stock when you start the evolution. So ultimately, we want to come up with a stochastic model of a stock price for a certain share on the stock market, and we want to formalize this the thing that we observe every day when we look into the charts in the newspaper or on the internet. And one way to model such a thing is to write down a differential equation by saying, okay, the evolution of a stock value should follow the following principle. It should have the following dynamics. And this is done by, here in this case, by formulating the so-called Black-Scholes stochastic differential equation. It says that the stock evolution should be given by the following two requirements, namely S naught, that shall be the stock value at initial time. It's a quantity which I can observe if I want to calibrate the model. And then I want to have a statistical model, if you like, of what happens in the future. And my statistical model is a dynamic statistical model. And it says that if I ignore this term, if I ignore this part, then it starts from claiming that in some way I do have an exponential growth, and alpha is the corresponding exponential growth rate for the stock. So if there was no randomness on the planet and everything would behave in a deterministic fashion, I would probably think that a stock price is something like a part of a certain population of a certain dynamics which behaves in an exponential fashion because success produces success, and we have this typical exponential behavior. And therefore my non-stochastic, so deterministic beginning of my model would be to say, okay, if there is no randomness at all, then the evolution of the stock should be an exponential growth evolution, and we all know that this is modeled by this exponential differential equation, which is solved by the exponential function. But now I want to be a little more realistic regarding my model, and I want to include also the effects of randomness. And here comes Brownian motion. So I want to think of a stock as being also subject to certain random pushes up and down kicks, basically, which are random kicks provided by increments of a Brownian motion. So that's some exterior force which acts on the market, any kind of natural disasters or stock correction or interest rate changes or whatever. So there's an exterior factor, which is BT, and the changes of the exterior factor impact on the value of the stock. And there's a proportional sensitivity of the total sensitivity of the stock value towards the increments or the changes of this, or the shocks which are provided by this exterior force. This is proportional. So the higher the stock, the more in proportional it should be sensitive to this. Should be sensitive to the excitations or shocks provided by the exterior factor. And then there's an overall proportionality constant which measures the precise proportionality of the sensitivity of the total stock price proportional to the size. And this proportionality factor is sigma. It is called the volatility. So that's my slightly improved non-deterministic model of the evolution of a stock price. And that's the Black-Scholes stochastic differential equation. It is called a stochastic differential equation, as we had already discussed at the beginning of this section on stochastic analysis. It's called a stochastic differential equation because it describes or tries to identify or single out a certain dynamics for S, here is stock price dynamics, by providing a rule for its infinitesimal increments, for the infinitesimal changes of this quantity. And the infinitesimal changes of this quantity are determined or are subject to infinitesimal changes of time, of course, but also subject to infinitesimal changes of an exterior random component or exterior random factor, which in this case is a Brownian motion. So therefore it's a description of a model through determining a law for its infinitesimal changes, and therefore it's called a differential equation, and since it features stochastic components, it's called a stochastic differential equation. And we want to take as a definition now the following concept of a solution of this stochastic differential equation, which will be extended in the theory later on without reference specifically to the financial market. We say that a stochastic process S is a solution to this stochastic differential equation if it satisfies the corresponding equation in an integral sense. Namely, if at any point t, the value of the stochastic differential, the value of this process, is given as the initial value plus the quantities which are obtained if I just take the integral of this infinitesimal changes over time. So this line here is just a formal description of infinitesimal quantities, which, at least as the infinitesimal change of a Brownian motion is concerned, are not yet perfectly rigorously defined, and we will not do it even in this lecture because we don't have to and because we don't quite know what it is. But we can convert this into a proper definition by converting this equality about infinitesimal increments into an equality which involves corresponding integrals along those infinitesimal increments, and we have invested a lot of time to make sense, to give sense to the integral on the right-hand side. So let me take away all these green lines, and let me start, if you like, a little bit over. So we want to produce a stochastic model for the evolution of a stock. We have at this level, kind of intuitive idea of how we would like to describe the statistical behavior, or the infinitesimal changes of this value as an effect of different forces acting on the stock value. And whereas this is only a formal description, we can convert this into a proper definition of a solution to this equation if we pass to the corresponding integral equation, which is just obtained by performing the corresponding integrals against these infinitesimal increments, which leads to expressions which we by now understand perfectly. So a stochastic process is called a solution to this Black-Scholes stochastic differential equation if for all times t we have an integral equality which involves on both sides of the equation this stochastic process, where on the left-hand side, since this is the integral with respect to stuff that happened in the past, the whole past of this stochastic, this evolution or this quantity is appearing. And the last result of today is the following proposition, which gives us an explicit representation of the solution of this process. Namely, it says this: the unique solution to this Black-Scholes stochastic differential equation, in the sense as we had just introduced, is given by the following explicit formula, namely S at time t is the initial value, which is a parameter, times the exponential of sigma times the Brownian motion at time t, plus in the exponent alpha minus sigma squared over 2 times t. That's the unique solution, in the proper sense, the unique solution of this equation. That's the proof of this will be the final piece of today's lecture. Okay, how do we prove that? We apply Ito formula, because this explicit thing here on the left-hand side is obviously an application of an exterior function to a two-dimensional process. And this ST, which is claimed here on the left-hand side, can be written as an exterior function f in two variables, and variables x and y, if you like, or t and bt, when f of x and y is the function that maps x and y into s naught, which is a parameter, times exponential of sigma y plus alpha minus sigma squared over x. So the two variables x and y are written here. Everything else is not dependent on x and y. This is just the three parameters of the model. So in that regard, the proposed solution here that is written here is obtained by applying this particular function in two variables x and y to a two-dimensional process whose first coordinate is just the t process, just the identity process, and whose second coordinate is the bt process, the Brownian motion in one dimension. Okay, I want to convince myself that this explicit function of two processes solves this stochastic differential equation in the sense that we had introduced. Okay, for that purpose, I shall apply the Ito formula, and the Ito formula wants me to compute the derivatives of this function f, the exterior function. Okay, that's now calculus. By this exponential form, the derivatives of the function f basically produce the function f again, but with an additional factor. So the x derivative of this exponential function produces this factor here, and the y derivative of this exponential produce the sigma as the prefactor. So in the end, I get a vector which is the function f multiplied by this constant vector. Now, I will argue below that for the Ito formula, which a priori requires the computation of all second derivatives of the exterior function, in this particular case, I need to compute only the second derivative in y direction, and that can be easily computed. It's then obviously just sigma squared, so 2 times the sigma times the old function f by a repetition of the previous calculation. Okay. Hence, let now xi t or zeta t, or xi, let's call it xi t, let xi t be in fact that composition of two things, namely the exterior function f applied to this two-dimensional process x, which consists in the first coordinate of the t process and the second coordinate of the bt process. These are two processes which are defined on the same probability space as the Brownian motion. The t process, as a matter of fact, is not stochastic at all, but nevertheless it can be understood as a process. Okay, and in fact I do have now, if I want to evaluate the evolution of this xi process, that's a prototype situation for the application of the Ito formula. Okay, xi t minus xi naught, according to Ito formula, is the first order derivative of the exterior function integrated against the two components. The two components are the t function or the identity function on the first component, so therefore I need to take the derivative with respect to the first coordinate and integrate it against the first coordinate process, which is the identity process or time process, and take the second derivative, the derivative with respect to the second coordinate, and integrate in the sense of a stochastic integration against the second coordinate process, which is the Brownian motion process. And then I need to compute all second order derivatives and so forth. But here again, okay, so the formula is here for the full case. I need to compute all second derivatives of the exterior function and integrate against the corresponding combination of a bracket. But what do I obtain if I take the first and first coordinate into the bracket? Then I get the covariation or the quadratic variation of the identity function, which is a function of bounded variation, so therefore the quadratic variation is 0. The co-bracket of the first and the second coordinate, or of the second and the first coordinate, is the co-bracket of the identity function and the Brownian function, which again is a co-bracket of a process of 0 quadratic variation and a process of finite quadratic variation, so therefore it's a 0 again. And the only thing that really contributes is the co-bracket or the bracket of the second coordinate with itself, which again is the co-bracket of Brownian motion, and that's the t process, the identity process. So inserting this into the previous consideration and writing out what I had computed for the derivatives here, which are here. So it's this derivative that need this derivative and this derivative. Correction, it's only the one of these, all these possible 4 derivatives, namely the second order derivative in the second direction only. I obtain, for the first part, this du integral, which was involving the first derivative and the derivative in the first direction. It's this one. And I have a direction in second order, a second direction, which is the sigma times and this is integrated against the Brownian motion. And then I get only one component from this second order correction, which is the second order derivative in second direction, integrated against the bracket of the Brownian motion, which is the u. Now, if I look inside the integrals, I see that in each of these integrals there is this f appearing again, but by my definition, f of u bu is psi of u. So in all these integrals, I can replace the f by psi of u, because it's just the same thing according to definition. And then I can just rearrange terms, because I see that I have a du integral twice, and the sigma squared and half here appears twice. So here I have a nice cancellation. And what I see is that for the du integral, I only have alpha psi of u du, and I have the sigma psi u by dbu. So I see that for all possible times t, the psi process satisfies the integral version of the stochastic differential equation. Of course, it starts at the right point, namely at S naught. So therefore, this explicit stochastic process, which is a transformation of Brownian motion using these parameters, that solves the Black-Scholes differential equation. And I can also show by a simple argument the uniqueness that there is no other process that solves that equation. Namely, I take, suppose I have 2 solutions to that equation, which start from the same initial datum, which I call xi1 and xi2. Then I can consider the difference of the two, call it zeta. So it's just a difference, and this is a linear equation. So I've taken the subtraction of the two, so then I easily find that the zeta process, just by taking the difference of the 2 equations and rearranging terms, I find that the zeta process solves the same equation. But now, of course, the zeta process starts at 0, because both zeta 1 and zeta 2 started at the same initial datum. So the difference of the 2 starts from 0. So in other words, I can also, just the same, I can also write just the corresponding integral version. I can write the zeta process as a solution to this integral equation. And can now also apply this integration by parts formula for the zeta process. Zeta is a product of 2 things. Zeta is the sum of 2 things. Let us keep this in mind. And but nevertheless, in particular, zeta is a semi-martingale, so I can apply my Ito formula in the simplest case, which is just the integration by parts formula. So zeta squared is 2 times the integral of zeta against itself plus the bracket of the zeta process. Okay, now I recall that the zeta process solves this equation, or it is a solution, is a sum of certain stochastic integrals. So therefore, by the associativity of the stochastic integral, I can replace this integration against the zeta by a sum of integrations against the corresponding components of zeta, where I have to respect this product rule, mainly. So d zeta in differential shorthand language, d zeta is an alpha zeta du, which is inserted here, and d zeta plus a sigma zeta u dbu. This is the infinitesimal shorthand notation for actually an integral equation, which is correct by the associativity of the Stieltjes integral. Okay, that was in writing out this first stochastic integral, and for the bracket process, I have a look again at the representation of the zeta here. So the zeta here is clearly represented as a sum of something of bounded variation and of a stochastic integral with respect to Brownian motion, and the co-bracket of two stochastic integrals is just the square of the integrands against the bracket of the stochastic integrators, or in other words, this bracket here is just sigma squared times sigma u times zeta u du. Okay, and I see that in this representation of the zeta squared, I have represented the zeta squared as a sum of a martingale, which is a sum of two things. One thing is a local martingale, which is this integral of something against a Brownian motion, which leads a local martingale. So the integral against a martingale leads a local martingale. And I have a certain du, have a sum of certain conventional integrals, which involve the zeta u part. In particular, if I hit the whole expression with the expectation operator, if I hit this equality with an expectation operator, everything that is a martingale will disappear. So therefore, I'm arriving at this formula for the expectation of the zeta. Namely, the expectation of zeta t at time squared at time t is 2 alpha time plus sigma squared times the expectation of zeta u squared du. It's just by pulling in the expectation operator inside the time integral. But this is now obviously a situation which calls for an application of the Gronvoll argument, the Gronvoll lemma, which tells me that in fact it's equality here, I'm just not even an inequality, which tells me that the expectation, so that's even equality, because that's correct for any time t, so in a way it's just an ordinary differential equation which this function solves, the function which is here defined as the map that takes t to this expected value of zeta squared at time t. That's just a real valued function, and what we see is that this real valued function solves the integral equality that comes with exponential growth. So therefore this function has also the representation as an exponential function, which involves the initial value of this exponential function times the growth part. So that's the exponential of this growth factor and so forth. But zeta was the difference of the two solutions, so therefore this function which we have here in this particular case at time 0 is 0, so therefore the zeta in expectation squared is 0 for all times, and which means that since zeta was the difference of the two xi1 and xi2, the two must be the same for all times. So we see that this explicit representation, or this explicit process, which was meant here, which is just an explicit transformation of Brownian motion, is in fact the unique solution to this Black-Scholes stochastic differential equation. And in order to connect to the actual practical object that is in the center of this consideration, I show you a few simulations, which here in this case are taken from Wikipedia. Here you see different simulations of such an explicit transformation of Brownian motion. You can do it yourself effectively using Excel or something. Probably I put that on an exercise sheet. Here you have different realizations of that geometric Brownian motion of this explicit process, given different values for the growth rate alpha and volatility sigma. And you see that this kind of is nice. And by the way, in particular, it is we see also by our explicit representation, you see that these processes, when they start at a positive value, remain non-negative throughout. We will discuss the Black-Scholes formula in the next session, or the Black-Scholes model at much bigger detail in the next session. when we will be dealing with this so-called Black-Scholes formula, which is the price of corresponding of certain stock derivatives which deal with such an S process as underlying stock price model.